All right, so hopefully it asks, does everybody have the recording symbol? All right, cool. So I guess let's just crack into this.
Oh yeah, Ross, just a quick note, the Beacon room is booked at 3:50, so we'll just have to make a quick 10-minute early escape.
Cool, no worries. Sounds like a plan. Thanks for the heads up. So just to get straight into it, a couple of quick things. As usual, please mute your microphone while the speaker is presenting. Save all your questions until the end, unless you have something that you really need to get out, and then put that into the chat and we'll get to it in the Q&A. Our speaker today is Marjo Verret from Victoria University of Wellington. Now, Marjo is from Canada. She did her bachelor's, her honors, and her master's degrees there. She's worked in the Yukon, British Columbia, the Northern Territories, Alaska, and Svalbard. So she apparently very much likes cold places. Not a surprise there, I guess. She decided to move to the Southern Hemisphere because obviously it's the best hemisphere, where she started her PhD. She actually just defended her thesis in March. So a big congratulations are in order for a job well done. So hooray for Marjo. Currently, she's working on biomarkers of ancient modern life in high elevations in McMurdo Dry Valleys. And unfortunately, she's going to be leaving us soon for the snowy glory of Svalbard. So congratulations on getting to move to a place that I would really love to go. If everybody would please join me in welcoming Marjo. Her talk is titled Beryllium-10 in Miocene Permafrost and the onset of persistent polar aridity in East Antarctica. So I'll let you take it away from there, Marjo.
Yeah, thank you, Ross. I'll try to just share my screen here. If we can go back. I have to go. Okay. Is everybody seeing this?
Yep.
Right, and I'll go in slideshow like this. All right, so everybody can see my screen now? Okay, cool. Yeah, so thanks, Ross, for the introduction. Yeah, I'm Marjo, and I just finished my PhD here at the Victoria University of Wellington at the Antarctic Research Center. My two supervisors were Warren Dickinson and Kevin Norton. And Cosmo was just a small part of my PhD. I did a lot of different geochemistry on really interesting core from the Freeze Hills in the high elevations of the Dry Valleys of Antarctica. And so, yeah, bear with me. And if some of the Cosmo stuff is technically inaccurate, please be nice. But yeah, here we go. And so I'm really interested in this general consensus that has been generally accepted, that the dry valleys have remained frozen for 14 million years. And so since the mid-Miocene. And so the overall idea there is that there's been no liquid water in the dry valleys of Antarctica for that much time, which we found hard to believe. And so we wanted to take a closer look into this. And so the McMurdo Dry Valleys of Antarctica are the largest ice-free region in Antarctica. They're in Victoria land. You can see it just pictured over here, just west of McMurdo Sound. And they're a hyper-arid environment with minimal liquid water and very cold environment. They're often used as an analog to Mars because of the such little amounts of water and of life that's present there. The mean annual temperature are around minus 23 degrees Celsius. I don't know if I can move this around. Yeah, and the mean summer temperatures are around minus 13 degrees Celsius, with precipitation generally below 10 millimeters of snow water equivalent. We also have this very interesting permafrost setup in the dry valleys, which is unique to this area. So normally in the Arctic, we have permafrost overlain by an active layer, a layer that thaws on an annual basis. However, in the dry valleys, we do not have, and especially in the high elevations, we do not have this layer that thaw annually, but instead we have this dry permafrost that remains below degrees Celsius, but that's deprived of any sort of water or ice cement within the pores. And this is due to an environment that's dominated by sublimation. And that just goes to show how dry this environment is. And so this is a type of environment we're dealing with, very dry. But the question again is, has this area been as dry, and how long has it been dry for? Oops. Okay. Yeah, and so in order to go back to the last time this area was quite humid or quite mild, we have to go back to the Miocene climatic optimum, which was about 17 to 15 million years ago. That was a time when global climate averaged 3 to 5 degrees warmer, and there was a tundra ecosystem in Antarctica, which is quite hard to believe in for anybody who's been there or has seen photos of the dry valleys. But yeah, there was no Nothofagus trees as pictured here on the right, and yeah, and so during this climatic optimum, we had a tundra environment in the dry valleys, but then it was followed by a period of climatic transition, which we call the middle Miocene climatic transition. And so this is where the questions arise. So was this period a sharp or a progressive cooling? And so I put dotted lines here on the graph, because there's kind of two contrasting ideas. The first one is that this middle Miocene climatic transition marked the onset of permanent polar aridity in the dry valleys around 12.9 million years ago. And there's kind of a new emerging idea that no, maybe this is not the case, and that the polar aridity occurred a bit further in the late Miocene. And so this is the kind of question we're asking. We're asking, when were the McMurdo Dry Valleys last wet? And so this is a picture up here in A of West Greenland, which we use as an analog for what the mid-Miocene looked at Freeze Hills. And here we have the Freeze Hills, or the high elevations of the dry valleys picture nowadays. And so we're wondering, when did this transition occur? And so we use meteoric beryllium as a tracer for water infiltration. We all are very aware of the technicalities of beryllium, but what is interesting about meteoric beryllium is that since it's brought to Earth through precipitation and accumulates at the surface, and it absorbs onto clay particles at most natural pH, we can actually use it as a tracer for water infiltration. And so looking at the concentrations of beryllium in a soil profile, we can actually go back and look at the time at which this beryllium was deposited. And this is what we find interesting in the dry valleys, because we have such minimal erosions. The surface have remained relatively stable since the mid-Miocene, and then we can use the concentrations of beryllium through a soil profile and actually go back and figure out when did it infiltrate, since it needs liquid water to displace. And so this is not my idea of doing this, of using meteoric beryllium as a tracer. It actually has been done twice before in the dry valleys. Once by my supervisor, Warren Dickinson. So Warren looked at two cores from a high elevation site in Table Mountain, and he found significant amount of beryllium. Here, I plotted these down, up to depth of 5 meters. And he found out that when he solved for closure time, he found that the closure time, or the time when water last infiltrated the McMurdo Dry Valleys, was around 6 million years ago. However, a study came out in 2015 and found meteoric beryllium within the blank range at about 60 centimeters depth. And based on this, they concluded that since there was no meteoric beryllium past 60 centimeters, that basically the last water infiltration was syngenetic, or the same time as the deposition of the sediment during the mid-Miocene. And the big question too that arose from this paper was the method that Warren used in 2012 too aggressive? And so they raised the idea that because Warren used a 6 molar HCl leach, a hot leach, for meteoric beryllium, it would have possibly liberated in situ beryllium and could have contaminated his results and have found higher concentrations of meteoric beryllium than there actually was in the samples. And so they suggested using a milder leach of 0.5 molar HCl and followed by an important step of 1 molar hydroxylamine hydrochloride to get both the amorphous oxide and the crystalline oxide fractions of meteoric beryllium. And so this leaching protocol has shown to fully recover meteoric beryllium without contamination from in situ beryllium. And so we thought that, okay, well, why don't we look back at these two sites, Freeze Hills and Table Mountain, and use this mild leach that has been widely accepted and see what we come to, which conclusions we come to. And so we're concentrating on site A and B here. And so A is Freeze Hills. There's different coring sites. Freeze Hills is this, when I talk about high elevations of the dry valleys, I mean above 1,000 meters of elevation. So Freeze Hills is in Inselberg at 1,300 meters above sea level, if I'm correct. It's at the head of Taylor Valley here. And Table Mountain is this mountain here at above that sits at 1,900 meters above sea level. And so why these sites are really interesting is they've basically been protected from erosion under hyper-arid conditions since their depositions during the mid-Miocene. And so they're very suitable for finding this timing of the onset from this warm period to the hyper-arid conditions we have today. And so the cores I use from Freeze Hills come from the 2016-17 Freeze Hills drilling project led by Richard Levy and Tim Naish. And so I use a series of different cores, mostly superficial cores, in order to understand the surface concentrations of beryllium. And so I have 12 samples from these preliminary sites in purple, and then 19 samples from a 5-meter core, which most of my PhD concentrated on. Actually, I had a lot of different geochemical analysis related to this core FHDP2C, so I know this core very well. And then I also did additional 10 samples from deep cores of Freeze Hills at 30 to 40 meters depth. And that was because we found a body of a large body or a relatively large body of ground ice, and we wanted to know if there was infiltration of beryllium associated to that body of ice. And so that's why we tested for the deep beryllium. And so additionally to the Freeze Hill samples, we also included the Table Mountain samples that were originally from Warren's work from field season in 1997 and 2000. So what we did is we ran 8 samples from the Table Mountain Core 1, and 5 of which were duplicates from the samples he had first run in the hot leach, because we were interested to see if we would actually if the criticism about the hot leach methods were valid. And so we did duplicates for this method. And then we also tested a few deeper samples. And so the idea is that when we have these 2 different sites, Freeze Hills and Table Mountain, and we have their concentrations of meteoric beryllium, we can solve for this one common variable, which is closure age. And so in order to do that, we have to make 2 assumptions, is that the flux is comparable at both sites. And so that's a relatively easy assumption to make since the sites are so close by. And that meteoric beryllium stop migrating in the soil at the same time, so that the closure age is synchronous. And so this is also possible or very valid to say if the meteoric beryllium stopped migrating because of climatic shift or a change in climate, because it would have happened at both sites in the high elevations of the dry valleys. And so then we have 2 scenarios in which that I would like to draw your attention to. So what we call an active scenario. An active scenario, so that's a scenario in which beryllium can infiltrate the soil, and so that happens when we have liquid water, an active layer similar to what we have nowadays in the Arctic permafrost. And so we have percolation or a seasonal percolation of water, which can carry beryllium through the soil profile, and then the migration stops at the ice table where we have permafrost. And we have a frozen scenario, which is what we have nowadays, in which the whole permafrost is blocked out, and that because there's no liquid water and it can't be carried through the soil column, we have a frozen scenario where the beryllium accumulates at the surface. And so if we know our surface concentration of beryllium under modern time, so N modern, and we can project N paleo by fitting an exponential equation based on our concentration profiles at depth. So that's the surface concentration of beryllium during the mid-Miocene, N paleo. The ratio of N paleo at Freeze Hills over the modern concentrations of beryllium should be both equal at Freeze Hills and Table Mountain. And therefore we can solve for, if we assume that also erosion rate is constant, then we can solve for closure time. And so that's the whole idea, using these 2 different sites. And so the first thing that we found is regarding the leaching method. And so remember when I said that the samples that Warren first ran in 2012 we're using a hot leach, a 5 molar HCl leach, in order to get the meteoric beryllium out of the samples. And so this was criticized because of the possibility of contamination with in situ beryllium. And so when we ran duplicates for those samples, and so Warren's samples are plotted in white in this chart here. When I reran some of his samples in 2019, I actually found more beryllium using the milder leaching method. And so that raised the question actually quite a bit more beryllium. We found concentrations of between 1.5 and 1.66 times higher. And so we were quite surprised by this, and we try to explain why. And so there's a few explanations that I would like to address. The first idea was that maybe it was because of the different AMS used for the measurements. So the first batch of samples during the hot leach were measured at GNS here in Wellington. And my new samples, my 2019 samples, were measured in Zurich. However, we know that interlab difference in measurements can only explain about 10% of difference, and we're seeing something up to 50%. And so we have to think a bit further. And one thing we kind of remembered is that the aggressive HCl leach does not include a step to leach the beryllium, specifically to leach the beryllium crystalline oxide. And so HCl tends to dissolve the most labile forms of beryllium, so the poorly crystalline beryllium oxides. But in order to get all the more complex beryllium oxides, it needs to be leached by a reductive dissolution. And so that's the hydroxylamine hydrochloride step in the second protocol that we use, and the protocol that I used. And so this could explain, this is a study by Whitman and all, and she found that in her samples, the crystalline oxide represented 20 to 45% of the fraction. And so knowing that, we assume that material with similar mineralogy would have the same repetition in the amorphous oxide and the crystalline oxide fractions, and hence we use this correction, the average correction factor or the average offset, in order to correct the whole Table Mountain data set. And then we were able to use the data set that Warren had in 2012. And so the concerns raised by Valletta, or the 2015 paper about the hot leach causing contamination from in situ beryllium could not be fully ruled out. However, we're quite surprised that we actually found more beryllium with our milder leaching method, which is something that's really interesting, and that we're wanting to look more into and to find out if, like, we just do the hydroxylamine hydrochloride step, what would we find? And we were trying to kind of playing with the idea of methods paper based on this finding. Anyways, this is a small parenthesis, but let's go back to what we're interested in. And this is the closure ages of associated to our high elevations of the dry valleys. And so here is the results that I found for my whole data set on the right here. So we have the Freeze Hill samples plotted in blue and our deep Freeze Hills plotted in orange. And then we have the Table Mountain sites plotted in purple. And so what I would like to draw your attention to is that we kind of have this we have three different groups. We have the near surface group, which plots up here, and we have this decay curve down here. Then we have another group down here, and then we have a deep group that plots down here. And if I do the statistics between the deep group and the lower group here, I do find that they're statistically distinct. And so that's why I separate these into three groups. And so the way we can explain this, or the way we can look at these profiles, is that we have to look at them at distinct active periods, or periods at which water could infiltrate the ground. So bear with me on this little explanation. And so if we have an active period in which beryllium can infiltrate the ground, we'll get this first decay curve. However, if this closes off and we have a subsequent active period, it will basically overprint what we initially had, causing this separation between our two profiles, which would ultimately look like this, which is kind of what we have actually here in our upper zone. So we have a first decay curve, then a little shift, and then a second decay curve. And so the idea is that for if we have multiple active periods, it is possible to find closure time for each individual period by projecting what our surface concentration would have been at that time. However, we found that it was quite hard to do this with lower samples because of the impossibility to find the shape of the curve. We have no idea of because we have such a straight line down here, it's very hard to project, but technically you could find the closure age for the lower groups. However, I'll concentrate on the higher group because that's what we're interested in here. And so if we project, as I said, if the surface concentration of beryllium for both these sites, and we assume that they close at the same time, then we find that for the upper group we have a closure age of 6 million years, and so not 12.9 as was expected, or what the literature seems to be saying. And the closure age in the lower section will keep it quite vague today because of, like I said, the complications we have of projecting our surface concentration. So anytime between the mid-Miocene and 6 million years. However, what we're interested in is really that closure age, that 6 million years, that seems to show that there was liquid water in the dry valleys at 6 million years. And so in order to get the superficial values during the mid-Miocene from meteoric beryllium, we need to find an erosion rate, and our erosion rate fit wide between the erosion rates that are common for regolith and the dry valleys. And so we know that our erosion correction for our modeling is realistic because it falls right between what is expected in the dry valleys. And so another thing I would like to point towards is this segmentation, or like the point at which the curves break, or I guess in my previous slide, it would be this red line here. And so this is basically the paleo-active layer depth. And this is very important because active layer and mean annual temperature are actually related. So you can solve for paleo temperature based on paleo-active layer depth. And so that's something that's quite commonly done in the Arctic. There's a simple Stefan equation in which you can get active layer based on temperature. And so we use this simple model that's basically a inverse, solving for the inverse, so using our active layer thickness, find the mean annual temperature. And so this model is called periclim, and we wanted to see how periclim did by trying to find out if periclim could recreate modern climate data. And so we inputted active layer and tried to see if we could find the mean annual temperature, and we compared what periclim found to the modern weather stations, and it does pretty well actually at finding out mean annual temperature based on active layer. And so we modeled based on our active layer thickness at Freeze Hills, and we get a projection here for our mean annual temperature that's around between +7 and a mean annual temperature around -10 degrees Celsius, and a mean summer temperature between 7 and 10 degrees Celsius. So this is quite a bit warmer than the -23 mean annual temperature we have nowadays. And so this is very interesting because this is quite a new finding compared to the overall idea that the dry valleys have remained frozen for since the mid-Miocene. And so, however, this is not surprising because it actually is in line with other regional proxies from coastal regions such as the Ross Embayment, Fritz Bay, and Toten Glacier region. There's open sea conditions in some of the andril cores during that period. And so the onset of persistent polar aridity in the dry valleys would coincide with a late Miocene cooling more than a mid-Miocene cooling. And so we would have absence of liquid water since 6 million years, contrary to what the overall literature said. And so this is critical to our understanding of the overall response of glacial systems in Antarctica, and including the East Antarctic Ice Sheet. It's also really interesting for paleobiology. It's also interesting in order to for future predictions, how will the dry valleys respond to climatic change. It's also really interesting just to all different geologists that have been in the dry valleys to put a different pair of glasses on, and not to take this landscape for granted and think that it has been frozen in time for 14 million years. And so I think this is a very important finding, and we're hoping to publish it after tweaking a few of the different graphs we have here. And so, yeah, thank you for listening, and I hope you enjoyed my talk.
Thank you. That was wonderful. Let's give her a round of applause, folks. Very nice. Do we have any questions for Marjo? Looks like Jacob has one.
It was great to see the data, especially from Table Mountain, Marjo.
Mm-hmm.
We have a in situ core from Table Mountain, which has an offset just like the one you're talking about. It's not quite as deep. It's between 0.5 and a meter, but interestingly, with the in situ data, we're seeing that paleo-active layer, a similar pattern. We can't get an age from that, obviously, but we're just working through erosion rates and things. But it is really interesting. So it's more of a comment, but maybe something for us to keep talking about offline.
Yeah, thanks, Jacob.
Nice. Anyone else? So I guess I have just kind of a conceptual thing. Can you think of kind of the thickness of the active layer almost like an unconformity in rocks, where if you have a smaller kind of active layer, say 10 million years ago, and then you have that kind of thicker active layer 6 million years ago, you erase that previous active layer signal. Do I understand that correctly?
Yeah. So your more modern active layer overprints your older. Yeah.
Mm-hmm. Okay, cool.
Exactly. Yeah. So our active layer basically shows, or the closure age is the last time beryllium infiltrated at that depth, and so it's the deepest. Yeah.
Right.
And actually, the active layer is quite, I didn't mention this, but since we're talking about active layer, it's quite deep compared to what we have in the Arctic, and so it was quite hard to model because we have an active layer that's 2 meters. You would not find that in continuous permafrost normally in the Arctic. However, we have no vegetation. Vegetation cover is really important in order to insulate, and for insulation at the top of the soil or the permafrost, and very minimal snow. And so those two things actually changed the thermal regime of the active layer, and explains why we have such a thick active layer with still very cold conditions during the late Miocene.
Okay, I have a couple of questions.
Yep.
First of all, the surface concentrations at the two sites are rather different. Is that just reflecting erosion rate?
I think surface concentrations are quite different at the different sites. I think it has to do more with the type of, I think we found a lot of this, especially like we looked at another site, University Valley, which is it's a valley, and so it kind of acts as a catchment. I think winds have a lot to do with its surficial concentrations. And so the other thing that we have, since we're comparing like the same profile and the same surface concentration, and just like time is a factor, we're kind of we're making also the assumption that the concentration which affect the superficial value don't change also with time. I guess that's the other thing. And so yes, there is difference inside, and I think there are localized differences like katabatic winds, and I think superficial concentrations of beryllium vary quite widely in the dry valleys.
Second question was that one normally thinks of meteoric beryllium-10 as sticking rather firmly to the soil grains. And not being particularly mobile in water. So this concept that the water is carrying it down through the profile that happens at low pH and under acidic conditions.
And so no, it's being carried, we're assuming that it's being carried like as a particle, like it's being carried through water infiltration, not that it's in solution.
Okay. So you've got some mechanism whereby the grains themselves are moving.
Yes.
So how do you envisage that happening?
Just carried through like a mechanical process.
Okay.
I was also wondering about the assumption of ice over. So this is kind of the work, the analysis you did and the interpretation is based on the assumption that there was no ice overriding the sites.
Yeah.
During or since the mid-Miocene. Would you be able to, well, I guess the first question is, can you pick out in your analysis whether or not ice override the site or not? And then the second question would be, what would be the implications of the record if you did have ice overriding the site during the kind of mid-late Miocene?
Yeah, it's a good question. I mean, it's just based on the overall regional knowledge that we have of the dry valleys, that we know like ice has not overridden these sites. The other thing too is that if we actually trace back the concentration of the lower sections, yeah, I don't know how to answer that question other than the fact that no, we come with the assumption that ice has not overridden the site just based on the local the regional geomorphology. We know that these sites has not been overridden. Our erosion rates too are quite low, and so I suspect that if ice had overridden the site, we would have higher erosion rates overall and high elevation sites. I mean, I think, yeah.
Yeah, okay. So it wouldn't change your profiles at all?
I have to think about this a little bit. Sorry.
Sorry, it's me just coming from ignorance, if anything, of this sort of work. So
yeah, no. I mean, if ice overrid the site, I mean, if it's since the closure time, it wouldn't affect. If it's before closure time, yeah, it could. We're making the assumption that the surface has been unglaciated. Do you have a comment on that, Kevin?
At Table Mountain, we've got surface samples that plot within the banana. So the assumption is that there hasn't been, and yeah, we have. Obviously, at Freeze Hills, it'd get it'd be too old. All the boulders are rotten there, but yeah, all of the samples that we have on the surface at Table Mountain illustrate that, Rich.
I mean, we have I think we have 40 centimeters of erosion since during millions of years. We have very minimal erosion rates. My guess is that if we had ice overriding the site, we would have way more erosion. But do you have a comment on it, Kevin? Or?
Yeah, I think from the meteoric point of view, it doesn't actually matter how you seal off the system from the atmospheric deposition. So whether that's through freezing up the ground or covering it with ice, I think that would end up looking the same. So you could say closure or ice cover.
Yeah.
Maybe. But yeah, it sounds like Jacob's got the best data to support the no ice past the geomorphology.
I'm happy with that.
Let me just put it out there for the geomorphologists amongst you. I mean, if you've got liquid water, then presumably you have freeze-thaw situations in the course of the year. Is that sufficient to move soil grains around? I would suspect it might be. I mean, here in Australia, for example, you depend upon termites to move them around. You don't have termites in Antarctica, I don't think.
Yeah, Warren Dickinson did a lot of work on polygonal sediment turnover in these areas using kind of a combination of a.s.l. and whatever other means he could get. And there is definitely sediment movement. Presumably it's something permafrost.
Yeah, freeze-thaw cycles, cryoturbation can move particles. There's all sorts of work being done by how, you create, even polygonal ground is formed by sorting of particles, and that's created through freeze-thaw cycles. Yeah.
But if you have freeze-thaw, then you have liquid water. So.
Yes.
Nice. Do we have any
The
more
thawing
questions?
doesn't occur at the high elevation though. It's freeze and sublimation.
Okay, but well,
Yeah.
this is another part of my PhD as well. But so there is liquid water in the modern dry valleys right now, and we know this through looking at the isotopes and the ice, but there is very little amounts of liquid water, insufficient to remove particulate matter. And so it's more like molecular water. And so it's enough to like move salts through dissolution, but not enough to move particles.
Good deal. Do we have any more questions or comments for Marjo's wonderful talk?
I guess just another thing I was thinking of is that with your profiles,
Yes.
you're able to like statistically say that they don't fit a simple exponential curve. I don't know if I missed that. So to kind of like rule out just a normal, you know, your first profile, active profile, and to kind of rule that out and say actually that's not feasible based on the data. Therefore, we've got a cutoff point.
You mean, oh yeah, between the two different profiles?
Yeah.
Yeah, that was done statistically, yeah. The segmentation, like the part where we have like the upper curve and then we have that was done statistically, yeah.
Okay. I look forward to reading the paper.
Very nice. Do we have any further questions? All right, sounds good. Well, let's everybody thank Marjo for her time and her wonderful talk today. I think we will move to, I think Aiden has a couple of things to talk about, and I can mention some of the stuff that happened last night after EGU, if people want to get into that a little bit as well. It was part of the stuff that I sent out in that big email before the talk today, but I'll let Aiden take over for a little bit.
Yeah, I guess just before we move into any updates or anything, does anyone have any topics that they'd like to bring up, any new research or successes or anything that they'd just like the script to hear? No, that's okay. Always like to check. Cool, so the next presenter will be on May 20th, and that's going to be Kari Rand. He's going to be given the talk that he was trying to give us a few months ago, but couldn't get a good connection with us. So thank you for volunteering again, Kari, and we look forward to hearing from you next month.
Do you want to give us a quick little preamble of what you're going to talk about?
So I'm going to be talking about some of the work I did during my master's, looking at using beryllium-10 and in situ radiocarbon to identify recently or geologically recently plucked patches of bedrock that are exposed in a glacial forefield, even if they don't bear geomorphic indicators of plucking.
Nice.
So look forward to that. Other things are, actually, it might be better if you bring this one to us, Ross, because there's a Cosmo reading group that's some folks are trying to start up, but Ross, you actually spoke with or communicated with them. I wonder if you could.
Yeah, I can definitely talk about that a little bit. So I got a hold of the two folks organizing this earlier in the week. I think it was like Monday. It doesn't matter what day it was. But it's going to be a bi-weekly discussion group where, people agree on a paper and then, everybody talks about it. And they're happy to, so one's based in the US, one's in the UK, and they're happy to kind of shift the times every other week so that they can capture like Europe and Africa pretty well, and then shift and kind of capture us and Asia pretty well. And it seems like it's a good opportunity to get to know people, to further our own understanding of the science and kind of the most current research that people are doing outside of kind of our little bubble. yeah. So if you want their contact information, get a hold of me. And I know that they're keen to get some people. It would be great to have a good showing from this part of the world. So yeah.
Sweet. I guess then the last thing was just to bring back up those workshops around the EGU, the Cosmo workshops. Is there another one tonight, Ross, or is it the last one was last night?
The last one was last night. And there was a fair amount of pretty good discussion until quite early in the morning for us. Yeah. So what all did we talk about? That's why I wrote the email, and I can't think of everything that was in there. There was a lot of really good discussion around kind of bolstering the community in general. There was a suggestion to have either once a month or twice a year workshops, online workshops, where new people getting interested in the science could learn new techniques, learn new skills, and kind of get to integrate with the community a bit better, get to know people outside of kind of their little lab group, which I think is a great initiative. Yeah, I think that was probably one of the most impactful things that came out of that. There was also some discussion around actually putting together, like the community putting together a document that has kind of our impacts when we go and sample something. So, photos of, what different methods to collect rocks look like, cutting it with a saw and then chiseling it all out, versus using, and I can share the link with everybody if they're interested, or anybody who's interested, drilling a couple little holes and then sticking or pounding some quarry pins in to actually like peel a flake of the rock off, which I think would actually benefit us all, so that there's kind of a common bank of knowledge that we can use to talk about, or to think about processes that we want to use to actually get rock, as well as when we go to apply for research grants and all that stuff, and we're asked about impact. We actually have a document that the community has put together that says this is what the impact is. This is the kind of gold standard for our community in reducing that impact. So I think there's a lot of good discussion around that as well. Then, yeah, we talked about a lot of stuff. Sorry about that. Let me see. We have a few new members as well. None of them are here today. And the last thing that I wanted to mention, so I came across this yesterday. There's I guess it's an online tool called GatherTown that it's basically an easy way to communicate with people. It's almost like a little game, but you have like your own little video there. So I was thinking that we could we've talked about, and we haven't really had a good solution to actually getting this to work, but having a forum where people can talk about lab issues or struggles that they're having or successes that they're having, and something like this could be a way forward in that regard. So it's kind of up to the community here to decide if we want to approach that with any real seriousness. I put one together because it was easy, so you can have a look at it. I can send the links out for that after the meeting if people are interested. Yeah, I think that was pretty much everything that came out of the EGU discussion last night. I mean, without getting into the esoteric details of AMSs and the different processes that people are actually going through to add niobium to hydroxide or oxides for beryllium. There's a pretty interesting discussion around that, but if you're interested, I can chat with you or point you to David Fink or one of the other scientists who actually does that work. So yeah, I think that's all I have.
Cool. I think it'd be quite cool if we do get some sort of channel up for more lab-based discussion.
Yeah.
But yeah, it really depends on how interested are the people in this group to actually use that sort of forum. Yeah. All right, thanks everyone for attending, and thanks Marjo again for sharing your research with us this week. And I guess we'll see everyone